Welcome along to the next video in this series called Exploring the Solar System. My name is Dr. Alan Wood and I'm a senior lecturer in the physics team at Nottingham Trent University. So what we're going to be talking about today is a session called The Mass of the Earth. So what have we been talking about so far? Well, in the last session, we're talking about Kepler's laws, about how planets move. And Kepler's first law is a planet moves in elliptical orbit with the sun at one foci. And then the second law is a line from the sun to the planet sweeps out equal areas in equal times. So it means the motion of a planet will be rather like this, in this ellipse. And it means its speed will vary. So it means it'll take a certain amount of time to get from this green line here to this green line here, and the same amount of time to get from this green line here to this green line here. And of course, those distances are different, therefore the speed varies. We're now going to think about Kepler's third law. And at the end of the last session, I gave you a question. I said, these were the data available to Kepler. Here's various planets, here's their orbital periods, and the semi-major axis. So the semi-major axis is roughly like the average distance from the planet to the sun. So if we just plot period and semi-major axis, we get a plot like this. So I've included not just the data from that previous slide, but other planets within the solar system as well. If what we do is we do period squared and semi-major axis cubed, then suddenly we get a straight line. And this is what Kepler found. And if we now look at this on a logarithmic scale, we can see all the planets there lining up all the way across the solar system. And we see this line nice and straight all the way along. And this is Kepler's third law, that the period squared is proportional to the semi-major axis cubed. So what does it actually say? It says the square of the period of an orbit measured in sidereal years is equal to the cube of the semi-major axis of the orbit measured in astronomical units, where 1 astronomical units is the mean Sun-Earth distance. So that's Kepler's third law. So Kepler's laws tell us about what happens, but they don't tell us why. And it's Newton's laws that then tell us why. And the most important of those, for the purpose of this session, is Newton's law of gravitation, which says that the force between two masses equals m1, equals the multiplication of the masses of those objects, where those masses are in kilograms, divided by the distance between them squared, where that distance is in meters, and all multiplied by some constant, Newton's constant of gravitation, which is 6.67 times 10 to the power of 11 per meter cubed per kilogram per second squared. Now, what this means is with one distance and one mass, we can scale the solar system based on Newton's law of gravitation and based on Kepler's laws about the motion of the planets. If we know one distance and one mass, we can scale the solar system. How do we get any one distance and any one mass? It's not terribly easy, for example, to take the Earth and put it on a balance. How do we weigh the Earth? Well, this is something that Henry Cavendish really wanted to find out. And so what he wanted to do is he wanted to find out the value of large g from Newton's equation, Newton's constant of gravitation, because from that you could weigh the Earth. And so he set up an experiment like this. So what we've got here is we've got small masses, here shown here 2-inch lead spheres, and we've got some large masses. And these small masses are separated by a 6-foot pole. Over here are much larger masses, 12-inch lead spheres, each weighing about 350 pounds. And so his idea was that there'd be an attraction between the large and the small lead balls. And so this fiber, which supports the 6-foot pole, would twist. And then if you shone a light on this mirror, and then looked at where the reflection of that light was going, that would amplify the change, and so a measurement could be made. And then the large lead balls could be moved. So rather than at this position here, they would go to this position here. So they move from here to here and then repeat the experiment. And that would allow the force of attraction between the lead balls to be measured. That would therefore allow large g to be measured, because if we've got the force of attraction, we know the masses and we know the distances, from this equation we can measure Newton's constant of gravitation. And then once we've got Newton's constant of gravitation, if an object of known mass is dropped towards the Earth, we can measure the acceleration due to gravity, and hence we can get the force. And that will then let us determine the mass of the Earth from this equation. So what Henry Cavendish did, it allowed us to come up with the mass of the Earth. So this experiment here lets us determine large G. Then what you're effectively doing is repeating the experiment, but now by dropping an object, it might be a pen, it might be a rock, towards the Earth. In that case, we can determine F by seeing how fast that object accelerates. We know D because the radius of the Earth has already been found. We know Newton's constant of gravitation. We know the mass of the object we're dropping. So the only thing we don't know in this equation is the mass of the Earth, and therefore we can find it. And that's what Henry Cavendish did. So he did this and he established the mass of the Earth. And the mass of the Earth is about 6 times 10 to the 24 kilograms. So we said if we can scale the solar system, if we can know the mass of one body in the solar system and the distance between any two objects, then we can scale the solar system. So Henry Cavendish let us get that mass. How can we go about getting one distance? And I'm going to pose that as a question. I'd like to have a think about that. And the distance we're going to establish, or the distance that was first established, was the distance between the Earth and Mars. And it was done by using 2 observatories at the Earth. So I'd like to have a think about that, and we'll talk about how that was done in the next session. Thank you very much for your attention, and I hope to see you in the next session.